In today's review, we dive into a shocking and unprecedented event that has shaken the foundations of Israel's military and scientific establishment, an accident so devastating that its consequences extend far beyond the borders of the country itself. The story centers on the catastrophic explosion at Israel's nuclear test facility, an accident that has resulted in financial damages estimated at over 700 trillion rupiah and exposed critical weaknesses in a program once thought to be operating with flawless precision and control. To understand the scale of this disaster, we need to walk through what the plant was, how it functioned, what went wrong, and why this mistake has now become a textbook example of the risks involved in high-stakes weapons development. The facility itself was not just another research center. It was the beating heart of Israel's nuclear ambitions, a sprawling and highly secretive complex located in a remote desert area, equipped with state-of-the-art laboratories underground, testing bunkers, containment domes, and massive cooling systems designed to regulate the extreme temperatures generated during nuclear experimentation. The plant had been built over decades, expanded with billions of dollars in investments, and was considered one of the most sophisticated nuclear sites outside of the major global superpowers. Its architecture combined hardened concrete shielding several meters thick, radiation-proof vaults, and advanced digital monitoring systems designed to provide early warnings of any instability. In terms of design elements, the plant was a fusion of military-grade security infrastructure and cutting-edge nuclear science, showcasing Israel's determination to maintain a technological edge in the region. When we talk about key features of this facility, we're looking at several unique components that made it stand out. The test chambers themselves were reinforced with layers of lead and boron shielding, meant to absorb stray particles and reduce radiation leakage. The control systems operated through redundant circuits, ensuring that no single failure could trigger an accident. The plant's cooling towers and liquid metal cooling loops were designed to dissipate extreme heat, while robotic arms and remote-piloted cranes allowed scientists to handle fissile materials without direct human exposure. These were the selling points of the plant, the reasons why it was marketed domestically as a near-indestructible asset. Yet as this disaster has now proven, no amount of engineering can fully compensate for human error. And it was precisely a sequence of human mistakes that caused the explosion. Reports from insiders indicate that the accident stemmed from a calibration error in the enrichment system, a seemingly minor miscalculation that spiraled into catastrophe. Engineers were attempting to adjust the pressure and temperature levels within a containment chamber, preparing for a controlled subcritical test. However, a software misconfiguration allowed a buildup of excessive neutron flux. The plant's automated sensors flagged the anomaly, but by the time technicians attempted manual overrides, the chain reaction had already gone out of balance. Within minutes, the system overheated, leading to an explosion that ripped through multiple test bunkers. What was meant to be a precision-controlled experiment turned into a self-inflicted disaster, destroying core infrastructure and scattering radioactive debris across a wide area. Performance aspects of the plant had always been a source of pride for Israeli officials. They boasted that the site could conduct tests faster, with greater precision, and at lower costs compared to similar facilities worldwide. The use of AI-assisted monitoring and predictive analytics was considered a groundbreaking feature, enabling scientists to forecast potential anomalies hours in advance. However, in this case, the AI system did identify irregularities, but the reliance on automated safety mechanisms created a culture of overconfidence. Operators assumed the system would resolve minor fluctuations on its own, delaying the human intervention that might have prevented escalation. This exposes a key lesson about overdependence on technology in high-risk environments where human judgment remains irreplaceable no matter how advanced the algorithms. The immediate impact of the explosion was devastating. Entire sections of the facility collapsed inward, firestorms swept across the compound, and underground tunnels designed to contain radiation were breached. Satellite imagery later revealed enormous craters, with smoke plumes visible from dozens of kilometers away. The financial costs, estimated at 200 trillion rupiah, or roughly 45 billion US dollars, includes the destruction of equipment, loss of research data, environmental cleanup, and compensation for affected communities. Beyond the material loss, the event has shaken global confidence in Israel's nuclear stewardship, raising concerns about safety standards in one of the most volatile regions of the world. When reviewing the unique design elements of the plant, one detail that stands out is its modular reactor cores. Unlike traditional test facilities, Israel's plant used compact modular cores that could be swapped and replaced after each experiment. This was meant to enhance flexibility and reduce downtime, giving the facility a competitive edge. Yet it was precisely the modular system that contributed to the accident, as the calibration protocols for switching cores were more complex and prone to error. Analysts now argue that the drive for speed and efficiency compromised reliability, a trade-off that ultimately proved disastrous. Another feature worth examining is the plant's containment dome. Inspired by designs used in civilian nuclear power plants, the dome was a massive reinforced structure meant to withstand both internal and external blasts. But the dome was engineered to contain controlled events, not a runaway explosion of this magnitude. When the chain reaction spiraled, the dome absorbed some of the initial shock but quickly cracked under sustained pressure, allowing radioactive gases to leak into the environment. This points to a design flaw. The reliance on civilian containment models in a military-grade testing context where risks are far higher. For layman viewers, it's important to clarify why this mistake was so consequential. Nuclear testing is not just about detonating bombs. It involves simulating nuclear reactions, calibrating warhead designs, and experimenting with materials at the atomic level. Even a small error in pressure, temperature, or timing can destabilize the entire system, much like how a tiny imbalance in a rocket's trajectory can cause a launch failure. What makes the Israeli case so alarming is that the accident wasn't caused by sabotage or external attack, but by its own mismanagement. In other words, the plant imploded not because of enemies, but because of overconfidence and procedural shortcuts. From a technical standpoint, the performance evaluation of this facility will likely become a case study for nuclear engineers worldwide. The redundancy systems worked partially but failed to prevent the final explosion. The cooling systems operated at maximum capacity but were overwhelmed by runaway reactions. The robotic safety measures removed some personnel from harm's way, but could not stop the destruction of infrastructure. This balance of partial success and ultimate failure highlights the complex interplay of design, technology, and human error. The unique selling point of the plant's supposed invulnerability was undercut in the most public and humiliating fashion. The political consequences are equally severe. Israel's adversaries are seizing upon the disaster as evidence that its nuclear program is less advanced than claimed. International watchdogs are demanding greater transparency, while neighboring countries are expressing concern over potential radiation drift. The financial cost, already staggering, is compounded by reputational damage that may limit Israel's ability to secure foreign partnerships or investments in high-tech sectors for the domestic population. The incident has sparked debates over the risks of nuclear experimentation so close to civilian areas, with environmental groups warning of long-term contamination. When analyzing the broader implications, one cannot ignore the lessons for global nuclear policy. Israel is not a signatory to the Nuclear Non-Proliferation Treaty, which means its facilities operate without the level of international oversight imposed on other nations. This accident demonstrates the risks of unchecked nuclear development, where even advanced nations can suffer catastrophic failures. The unique selling point of Israel's nuclear program, its secrecy and autonomy, now appears as a liability rather than an asset. Transparency and international cooperation might have prevented the shortcuts and misjudgments that led to this disaster. Looking at the scientific aspect, the loss of data is perhaps the most underappreciated consequence. Decades of research, test results, and classified designs were destroyed in the explosion. Hard drives melted, archives incinerated, and servers obliterated. For a program that prides itself on precision engineering, this represents a devastating setback. Rebuilding the lost knowledge could take years, if not decades, setting back Israel's strategic edge in ways that financial compensation cannot repair. The plant was not just a physical structure, but a repository of intellectual capital, and its destruction represents an intangible but deeply consequential loss. From a technological perspective, the accident highlights the double-edged nature of advanced innovation. Israel's push to integrate AI modular reactors and cutting-edge containment systems was meant to leapfrog traditional designs and establish superiority. Yet these very innovations introduced new vulnerabilities. The AI created overconfidence, the modular system increased complexity, and the containment dome was mismatched to military realities. This is a classic example of how innovation without thorough risk analysis can backfire, turning strengths into weaknesses. The human factor is also central. Investigations reveal that staff had been working under immense pressure to accelerate testing schedules, with deadlines imposed by political leaders eager to showcase new capabilities. Fatigue, stress, and institutional pressure all contributed to lapses in judgment. In one striking detail, safety drills had been postponed in the weeks leading up to the accident because of time constraints, meaning that staff were less prepared to respond when alarms went off. This underscores how organizational culture can be as important as engineering design in preventing disasters. For ordinary viewers, perhaps the clearest takeaway is that nuclear technology is not forgiving. Unlike conventional accidents, where damage can be contained, nuclear accidents have cascading consequences: financial, environmental, political, and strategic. The explosion at Israel's plant is a vivid illustration of how even advanced nations are vulnerable when arrogance, shortcuts, and over-reliance on technology collide. What was once promoted as an untouchable fortress of scientific progress has now become a symbol of fragility, a reminder that in the pursuit of ultimate power, one mistake is all it takes to trigger unimaginable consequences.